Welcome back. Gibbs free energy is the topic for today. I think I'll use a black pen because it looks a bit better. From our rules of thermodynamics that we had before, we have an amount of energy that can be converted into different forms of energy but not destroyed, and we have some kind of entropy term, the amount of different states or something. We can formulate that into an equation, but let's go through it in a couple of steps. So if we take the energy in a system, we can imagine that it can be hot, so it can have some heat energy. It can do some work, so that would be another type of energy that it could have. Obviously, if it's not moving, it isn't actually doing work at that point. Then it can have chemical energy stored in some kind of bonds, and there's the entropy in the system which can change, giving us some of the other types of energy if it converts. If we do this, we end up with a lot of terms. So first of all, we've got the heat, which is the amount of joules of energy, because if we make our system heavier but the same temperature, it contains more heat energy, and so we need the energy in joules and not the energy in temperature, or the heat in temperature. So it's equal to the temperature times something to do with the heat capacity. Then we've got the work, which is force times distance, and that, if we're using a gas, would be to do with the pressure and volume. Then we've got the chemical energy, which we typically convert into one of the other two forms, and entropy, which we would call S. So now we can define the Gibbs free energy as the heat energy and the entropy. We've got a negative term in here conventionally, which we'll come on to in a moment. What I wanted to say, however, beforehand, is we've removed the term for work, because in this case we are considering a system, a chemistry type system, where the volume isn't allowed to change, like a flask. If we change the volume, we will need to use a different type of equation, and for practical reasons it becomes difficult to calculate when several of these things are changing at the same time, and therefore we typically go away from keeping the temperature or the amount of heat constant. So there is an engineering equivalent for an engine, for example, where the engine is doing work but it's not changing in temperature. So the volume is changing but heat is not changing. In the chemistry example, we're allowing the heat to go out through the walls of our flask, so the temperature is the same the whole time, and then we can have T as a constant in there. Otherwise, T is a variable, and then we have too many variables to be able to solve it very easily. So for practical reasons, we can think of cases where heat is allowed to escape, cases where the heat is changing, and cases where the volume is changing, and we need to consider those separately if we're going to think about it properly. We have a bit of a problem because we don't know how much heat there is in our system, so we can consider just changes. If we consider changes, we just need to add a delta for changes to our variables here. As I said, the temperature isn't changing in this particular case, so we're holding the temperature constant even if whatever we're doing is generating heat or absorbing it. If we consider that global entropy has to increase, we can see that we've got two terms. We've got the entropy of the system here, which is temperature multiplied by the entropy of the system, and we've got the entropy of the outside. In this case, if heat is given out to the outside, the entropy of the world will go up. That's why when we think, or when we do some work, we are decreasing entropy locally, which is a bad thing, but it increases entropy globally, and so the universe is satisfied, and our laws of thermodynamics stay unmodified. Now onto the sign. It doesn't actually matter which way the sign is, but we have to make them agree with each other. So if we take delta H, formally we say it's the heat in the system. So if it is giving heat out, then it's negative. So negative delta H means it gets hot, it gives out heat energy, so it's losing heat energy to the surroundings. If it gets cold, it absorbs heat energy from the surroundings because we have defined temperature as being constant. If we change the situation, we're going to have to use a slightly different form of this equation. The simplest use of this equation is to tell whether a process will happen on its own or not. So if we have our delta H being negative, that means heat is given out. That's typical for a process that will tend to work because we're increasing the entropy outside. Then our entropy inside going up will have to also make it better, and if we make the sign then agree, we will have to have a positive entropy, meaning entropy going up. So we've got to make these signs agree with each other with our laws of thermodynamics. So we can consider these cases. If we've got a negative enthalpy, delta H, then heat is going out of the system. The total amount of H is not known because we're only considering changes. If it's positive, then it's taking heat from the environment. It's easier to consider just the changes because we don't know how much heat there is in the system, or it may not be important to us. Likewise, with entropy, we don't know where the 0 point is, but we are considering if we add it, so we increase it, then more entropy is there, and if we decrease it, then less entropy is there. Because it's a change, we haven't defined where the 0 is. So if we take a simple case, let's take ice melting, then we can think about that in more detail. So now I've got some ice, it's a solid, and I've got some water, which is a liquid, and we're not going to worry about the change in gravitational potential energy of it getting lower, because that should also be there. What energy have we got? What does it change in heat? Well, heat is going into our block of ice. If I have an ice drink and I consider it to be very much like a chemistry vessel, because I'm not letting anything into it, I just leave it lying around, and heat goes in from the environment and melts the ice. So that would be plus delta H, and it goes to water. What we also know about the water is it's got molecules in it, and they are moving around, and in the ice they're not moving around. So we have a simple process that we can define fairly easily as being having a positive delta H and a positive delta S in this direction. If we freeze the water, then the opposite happens. We can also take it a little bit further, so we can say the delta S, the increase in entropy, is because the water molecules are free to move around. There are a whole lot more possible states, and so we expect an increase in entropy. And we can also say the heat is going in and it's breaking some bonds between the water molecules. They're not full bonds, but they are kind of bonds, and that will break them and allow them to move around. That gives us a reason for this heat to go somewhere, because the temperature is not changing. All of you should be aware that if you take a glass of water at 0 and you put an ice cube in there at 0, then it will stay at that temperature until all of the ice has melted. This type of reaction, however, has an important implication. Because the delta H and the delta S don't agree with each other due to this negative sign, so they're both the same sign, but we've got a negative sign in between, so this one is making our delta G bigger, the enthalpy is making our delta G bigger, and the entropy is making it smaller. We can see that in this case the heat going in is going to make it less likely to happen, and the entropy going up is going to make it more likely to happen. So we can deduce, without actually knowing it, that delta G is negative if the reaction goes. In science words, we call that spontaneous. It means it goes on its own. So if we have a delta G that is negative, then our reaction will go on its own. In this case, it's not strictly a reaction, it's just a physical process. We've got some ice, turns into water. The interesting thing about this particular process is that because these two terms disagree, if we change T, which multiplies our delta S, we can make the reaction go the other way. We know that because if we lower the temperature, water freezes. But now we have an equation that describes exactly the correct process. As we cool, so as we reduce T, the value of T delta S goes down, and then the entropy that we gain from the water becomes less important, less significant, compared to the energy that we get from bonding the particles together and heating up the environment. So if our environment is below 0 degrees centigrade, then this reaction will not be spontaneous, ice won't melt, and indeed if we get it cold enough it will go back the other way. So if we hit exactly 0, nothing happens, and that's because these two terms are completely balanced, and if we go below 0, it goes the other way. If we think about it a little bit more closely, we can see that in our ice we've got a bonding energy between the different molecules of water, and it can vibrate. In the water we've got rotational energy because the molecules can rotate, we've got translational energy because they can move around, and we've got vibration. So in a different way we can divide our energy up differently. Also, there is a lot more possibility here because we can have different values of rotational energy, different values of translational energy, and different values of vibration here, whereas the possibilities of both are very limited. The bonding energy is pretty fixed. This connects nicely to an experiment that we can do in the lab, where we have water and we cool it. If we cool water in something like salty ice, we are going to remove heat from it and change the temperature. So we're doing Gibbs free energy equations, but we're doing them one after another as we change the temperature. And we would expect, because the heat is going through the walls of the container, we would expect it to cool at a fairly constant rate. Then it will obviously cool off because it will reach the temperature of the salty water bath or the freezer that it's in. So if we do this experiment with something that isn't changing state, it just cools down. That's our base curve. If we now put some water in there, we might expect it to go down to 0 degrees and then stop going down, about this line, and put in black line. So it would stop going down and continue, because during this time, instead of the heat that's coming out of the liquid going into cooling it, it's going into making bonds. So we're making bonds, they are generating heat, and the heat is counteracting the cooling for a certain amount of time, depending on how much heat we have available, how much water there is in there, and then it will continue. That's exactly what happens in practice if we do that experiment. But not quite. If we choose a very clean container, something new happens. The temperature carries on to below 0, and then the water starts to freeze. When the water starts to freeze, the temperature comes back up to 0 very quickly, and it continues along the black line. So now we have three possible lines. We have the line where nothing happens, the line which is theoretical from our equation, because we are giving heat out from our process, freezing, and so it is stopping the temperature going down, and then it continues on the same line afterwards. And then we have the real curve. What really happens is it overshoots somewhat. Depending on conditions, it can overshoot by more or less. That shows us that there is something missing in our model. The thing that's missing from our model is a term to tell us how much free energy is required or is used up making a surface. That will make allowances for the process going past 0. It also explains why when we boil water it sometimes passes 100. The typical experiment for this, or the typical thing that you may have been warned about, I certainly was when I went to university, is if you heat up water in a microwave, it is possible to pass 100 degrees and it doesn't boil. And then, if you put a spoon in it, for example, it then boils and it can injure you. It's exactly the same thing as is happening here. We're going past zero, cooling it down, and the water is still liquid. And then it can start to form ice. And once it does, then that lower temperature is evened out by making more ice, so it forms a big chunk of ice quite quickly. If we're boiling it, we go past boiling, it can't form a new bubble because that costs energy. But when we get far enough past boiling, it suddenly bubbles very fast. It happens particularly in pure systems.